can go ahead and get started. Welcome, everyone. It's August 7th, the California Water Quality Monitoring Council's Microplastics Monitoring Subcommittee. I'm here with my co-chairs, Shelley Moore and Dr. Monica Araginzo. So we're going to jump right in. We've got a pretty packed schedule today. We've got some updates from our work group leads, but we also, before that, we've got some really exciting guest speakers here from Photothermal Spectroscopy Corp, as well as GoPert, to hear about some of the cutting edge technologies that's being applied to microplastics analysis. But before we do that, we're going to have a quick update from the State Water Board side about what we're doing on microplastics, drinking water, and elsewhere. And then also we'll hear from Caitlin Kalua from the Ocean Protection Council. So as a reminder, this is a community that is focused on open sharing of data, information, resources for microplastics and other plastic related topics. And so we have a Zotero library that is shared. If you want to be part of that, we can give you an invite. We also use a Google Drive folder to house all of our meeting recordings, slides, agendas, references. We've got a lot of really good stuff on there. You can check it out with the link here. And then anytime we were working with code related to projects, we like to make sure it's open source on GitHub. Our previous meetings, like I said, are recorded. You can find those either at the bit.ly link or on a YouTube playlist that we've made. Go ahead and check that out if you missed some of the previous meetings and you'd like to see what we covered. And I'm going to give a brief update on what we're doing at the State Water Board with microplastics. We have Senate Bill 1422 focused on drinking water, and we have a plan for 4 years of testing and analysis. Right now, we're wrapping up a lot of the research for our phase 0 that will lay the groundwork for issuing monitoring orders to about 27 water systems around California. And that's what this iterative approach looks like. Right now, we are working on getting some sampling methods validated for microplastics in drinking water, comparing the ASTM gravity-fed filtration method with an inline filtration method. And so the SOPs for that are going to be coming out pretty soon. We're also doing a little bit of range finding, figuring out how these methods perform in California's diverse drinking water source types with the different interferences that one might encounter. And then we'll also be holding a training session for anyone that wants to learn how to use the inline filtration method later this year. In addition to that, we're also developing a sampling analysis guidance handbook. Part of that effort is conducted through this work group. We're also providing time and resources for anyone that wants to get ELAP accredited. If a laboratory wants to discuss that process, we have a sort of ad hoc work group that can meet on that, but you can also send me a message and we can schedule an appointment to talk. Developing a data infrastructure, which we're going to hear from Dr. Wen Cowger about how that's going. And then a communication toolkit for water systems, which is also coming out of our work groups. So mentioned before, laboratory accreditation is available. Any laboratory from around the world can apply for accreditation and get accredited through ELAP for microplastics analysis. And in addition to all of that work, we are also doing some related work to microplastics outside of the drinking water context. So I mentioned the data harmonization reporting tool. That's specifically designed for drinking water, but it's also going to be applicable to any other matrices that we decide to use. Am I not sharing my screen right now? Oh, this whole time. I'm so sorry.
Oh, sorry, I didn't realize you had slides.
Everyone's like, what are you talking about? Sorry about that. So here we go. So in addition to the data harmonization reporting tool, we've got an ongoing project with SWIRP to standardize extraction methods for microplastics in animal tissue, dirty water, so ocean water and other complicated water matrices, as well as sediment. Finishing up that comparison project with sampling methods for drinking water, but then we're also figuring out how to standardize sampling methods for surface water, fish tissue, and sediment, again in collaboration with SWIRP and many other collaborators. So brings me back to my agenda for today. That's the State Water Board update, really brief. Next, we're going to go to Caitlin Kalua from the Ocean Protection Council. And apology for not sharing these slides earlier. Hopefully it wasn't too confusing. So Caitlin, I will hand it over to you if you are ready.
Absolutely. Can I have slide sharing or screen sharing?
Yeah, thank you, a co-host. Shelly, would you be able to make Caitlin a co-host? I don't know if I'm able to.
Caitlin, you should be able to show your slides now.
All right. Thank you. Let's see. Share. So, oops, I've got multiple screens going and it's not working very well. Give me one moment. Now you can see my slides, but I'm unable to see. Quick notes. Apologies, give me one moment. I'll stop screen sharing. We're going to give this another go. Well, with that, I'll just go ahead and dive in. Thank you, everyone, for your patience. My name is Caitlin.
If you go up to display settings and just do hit the swap screen button, then we'll see the not speaker notes version.
Oh, I'm so great at this. Where is that?
Display settings. It's right above the slides on the speaker view.
See.
Yeah, right there.
Remote control?
No. If you hit the drop down menu from display settings, there should be a swap presenter view.
I don't think she sees display settings.
I don't see it, unfortunately.
It's on the top.
Screens?
It's on the top. It's next to show taskbar. There you go.
There you go.
Oh, there it is. Wonderful. Thank you. Oh, much better. Okay. All right, we'll start at the beginning. Thank you, everyone, for your patience. Hopefully we can cut that from the recording, but for those at home, maybe you had a chance to grab a cup of water, a cup of coffee. Good morning. My name is Caitlin Kalua. I am currently Deputy Director for the California Ocean Protection Council, formerly the Water Quality Program Manager, and providing, of course, this agency update. So happy to see many familiar faces, but of course, for those who may be unfamiliar with OPC, just as a brief background, OPC is a cabinet level policy entity within the state of California. It is non-regulatory, but its mission is to protect and enhance California's coast and ocean through innovative science-based policy, innovative research, and making strategic investments through collaborative partnership. As I stated before, we're not regulatory, but our work falls under these 4 categories of climate change, equity, biodiversity, and supporting a sustainable blue economy. OPC has long advanced work related to plastic and plastic pollution, recognizing that plastic pollution, of course, is pervasive, it's persistent, and once it's entered into the environment, it's incredibly difficult, if not impossible, to remove. Our work falls under the strategic plan goal 3, that is to enhance coastal and marine biodiversity and enhancing coastal and ocean water quality. I apologize, I don't have notes on the presentation, so I'm a little winging it here. I apologize to everyone. Going to the next slide. OPC has, to date, OPC has prioritized funding a number of projects related to improving microplastic monitoring, as well as understanding microplastics in California's aquatic environment. This has included foundational research and investigation into microplastic sources and contamination into San Francisco Bay, in part performed by SFEI. as well as this trash assessment playbook to inform trash assessments, essentially for monitoring trash in California receiving waters, as well as a risk assessment framework that was published by the California Ocean Protection Council Science Advisory Team in 2021 that informed our preliminary risk assessment framework, essentially identifying the need to identify the highest emitting sources of macro and microplastic contaminants in the marine environment, identifying the trends of microplastic pollution, as well as directly linking and identifying microplastic sources. To that end, all these projects together informed the statewide microplastic strategy that was adopted by the Ocean Protection Council in 2022 that advances essentially a two-track simultaneous approach. One is identifying early recommended solutions for reducing plastic pollution in the environment, either through pollution prevention or pathway intervention, that is to intervene with the mobilization of microplastics into the marine environment, as well as advancing science to inform future action, essentially to inform our future solutions related to microplastics. Central and foundational to the research and priorities laid out in the statewide microplastics strategy is monitoring to understand, again, the occurrence, the trends, the sources of microplastics in California's marine environment to then inform risk thresholds as well as assessment. Again, there's more, the most prevalent sources as well as the pathways in which microplastics enter the environment, and then informing new solutions into this very circular structure. The statewide microplastics strategy outlines a fairly ambitious timeline for addressing microplastics in California, including prioritizing standardized methods, that is for both laboratory assessment, but also the field collection methods, initiating a pilot monitoring program, investigating sources and pathways of microplastics to again inform risk assessments and recommend source reduction strategies by 2026, in which the microplastic strategy is required by the legislature to report activities and findings done in California to advance the strategy. To date, to advance this foundational monitoring in California, OPC has initiated 2 projects related to plastics monitoring, simultaneous projects. One is identifying microplastic field sample collection. It's a field sample collection method evaluation and standardization study, ultimately with the purpose of developing standardized operating procedures or SOPs for sediment biota that includes fish tissue and shellfish, stormwater, as well as surface water in partnership with the State Water Resources Control Board. Simultaneously, we are just in the beginning stages of developing a statewide plastics monitoring plan. This is both to inform a pilot statewide plastics monitoring, leveraging existing efforts, as well as identifying future potential state, local, potentially citizens science efforts that can be leveraged into this larger plastics monitoring network that is both a pilot, but also a long-term phased approach to advance plastics monitoring that is both for large plastic debris as well as microplastics in California. We are just again in the beginning stages, but public engagement and you'll see more, I think, coming from this project in the coming months, within the next 6 months. Earlier this year, the Ocean Protection Council, as well as California Sea Grant, launched a request for proposals. This RFP was launched in February, essentially with 2 simultaneous research calls or priorities. One was a research call to increase the understanding of specific sources of microplastics in the aquatic environment, as well as understanding the ecological effects or potential risk thresholds related to microplastics, as well as then a second call related to informing the design, operations, and maintenance of low impact development or green infrastructure as one potential strategy to intervene with microplastics before it reaches the aquatic environment or California waters generally. This was a very, very competitive solicitation in which we have identified 5 projects to bring to the OPC council meeting that's taking place next Tuesday, that is August 15th, for 5 selected projects that were reviewed through a technical review panel, as well as very carefully considered using the selection criteria and the RFP priorities that have resulted in these 5. First 3 relate to that first research call related to improving our understanding of microplastics in California waters, as well as potential risks. And then the final 2 are related to informing both the placement as well as then the actual design and operation potential guidance related to designing low impact development or green infrastructure, BMPs, in California urban environments. We will be seeking a funding augmentation to advance all 5 of these projects. And so that again will be brought to the council for approval and concurrence next Tuesday. Outside of this excellent subcommittee and the community that I know Scott and the State Water Board has facilitated through the Water Quality Monitoring Council, I do want to share 2 additional resources for those interested in tracking OPC's efforts related to ocean litter and plastic pollution generally. That is both for large macro pollution, but also microplastics. That is a co-facilitated California ocean litter strategy. This predates the microplastic strategy that is co-facilitated by OPC and NOAA's Marine Debris Program. Highly recommend those who are interested in either attending public webinars, information sharing, as well as work group meetings related to ocean litter. There is a very specific listserv here, as well as a general OPC listserv to stay informed of our projects. With that is my email. Thank you all, and that's my update.
Thanks so much, Caitlin. We've got a little bit of time if anyone wants to ask any questions. People can feel free to raise their hands or just unmute in the chat.
Hi, Caitlin. This is Emily Clark. I'm with Eastman Chemical Company. In regards to the statewide microplastic strategy, within there, and please forgive me because I have not reviewed it recently, but I believe you were going to hold application-specific work groups, if you will, I think was how you termed it. Has any, and I know food service was one of them and something else. Have any of those meetings begun yet?
They have not, and I sincerely appreciate you bringing this to everyone's awareness and attention. There are, in the early recommended solutions, track 1 of the strategy, it does include these sector-specific workshops, essentially to evaluate the current state of the science, as well as potential solutions that are, again, very sector-specific related to food serviceware, vehicle tires, ocean-based debris like aquaculture, among others, and textiles, et cetera. And these are still in the scoping phase. The strategy did say by 2023. I think we're looking at more of a 2023-2024 timeline as we're identifying the best path forward. We're trying not to duplicate efforts with other agencies, essentially. And so we're still in the phase of identifying our partner, making sure that we are coordinated as we identify each of those sector-specific workshops. So more information will be shared, Scott, when we have those scoped and publicly available. This will be shared over this listserv potentially, as well as OPC listserv.
That is perfect. Thank you. I really appreciate that update. Thanks, Caitlin.
Absolutely.
All righty. If anyone has any more questions for Caitlin, you can drop them into the chat. Now we're going to go to our next speaker, which is Ting Yan from Photothermal Spectroscopy Corporation down in Santa Barbara, California, where they're developing some pretty innovative methods to analyze microplastics using optical photothermal infrared spectroscopy. So hand it over to Ting. You're on mute.
Yes, now I'm good. Thanks. I'm trying to pull up my slides. Okay, can everyone see my slides?
Yeah, did you want to do the screen?
Yeah, I will. Thank you. Thank you so much for having me here, everyone. So I'm Ting from Photothermal Spectroscopy Corp. So today I'm going to talk about submicron IR, optical photothermal infrared, which will come with the ability to provide also simultaneous Raman, and also collocated fluorescence for micro or even nanoplastics identification. So many of you probably already know that the microplastics or nanoplastics now are a major emerging contaminants in the environment. And many studies actually suggest that only the or most the smaller one, like smaller than 20 microns or into the nanoscale, plastics are the most physiologically irrelevant. However, now there's no broader consensus on how to prepare the sample and what analytical tools are to be used. Currently, there are some challenges with the tools. For example, optical microscopy, which doesn't offer chemical information. And for IR microscopy, it is chemically specific, but there's some issue with the spatial resolution and the spectral artifacts. And for Raman spectroscopy, or Raman microscopy, it is chemically specific and can offer better spatial resolution than IR, but it inherently is weak. And the fluorescence may overwhelm the signal, and sometimes increasing the laser power to get better signal can result in the sample damage. So today I'm going to introduce the optical photothermal infrared, for short, OPTIR, that will overcome the above mentioned challenges, and I will give some results that is from the microplastics sized from up to 200 microns down to 500 nanometers. So let me talk a little bit about of the IR microscopy limitation. Because of the longer IR wavelength than the visible laser, the spatial resolution from a traditional IR can be around 10 to 20 microns that can resolve like microplastic submicron features. And it usually requires complex sample preparation. And for ATR, FTR, it can offer better spatial resolution, but it will require the contact with the sample and make it difficult to target small particles. And it sometimes can have the problem of cross-contamination, and the tip of the ATR is not cheap. And for microplastics, saturating effect and scattering effect and or saturation can be a problem. So OPTIR overcome these problems. So how does it work? First, a pulsed and tunable infrared laser was focused on the substrate. For example, here, the brown substrate. You can imagine the blue are the microplastics you want to look at, you want to identify or get a spectra from. And because of the laser wavelength of the IR, the spots will be around 10 to 20 microns. And then conveniently, a visible laser, which typically, as an example here, 532 is focused through the same lens also onto the same substrate. But because of the shorter wavelengths, the size of this focused spot now is submicron. That is 30-fold better than traditional FTIR. And if there's IR absorption, and that will result in the thermal expansion or reflective index change of the blue spots here, for example, microplastics. And we can detect the reflective change of the green laser. And this by at the same time monitoring how the green laser responds while we tune the IR from A wavelength to B wavelength. This will create the IR spectra. For example, here, if there's some response here, if there's IR response, you got this peak. And if there's no response, you got here the baseline. And this is indirectly measure the IR absorption. And this will, but it's from the submicron spatial resolution. And the spectra usually can be connected in seconds or even less than 1 second. And for several spectra to average to identify the particle, that typically requires about 20 seconds. And or because the IR laser is tunable, you can tune it to a fixed frequency and then map out where the chemical functional groups, where are they and the abundance of them, or you can connect a hyperspectral imaging for the region of interest to identify from spot to spot what are the chemicals. You don't lose anything in that case. So this is how the OPTIR works, and to get this submicron spatial resolution. And as I mentioned before, we use a 532 nanometer laser. And if the Raman scattering is happening, it's happening for free. So what we do is just insert a filter here, and then to direct the shifted photon into a Raman spectrometer. By doing this, we can connect the IR and the Raman spectra from the same spot at the same submicron resolution, also at the same time. By combining this IR and Raman into one instrument, this gives a chance to leverage the complementary of IR and Raman, because for some material, it's IR active and Raman inactive, or Raman active, IR inactive. Or if they are both active, IR can be used to confirm Raman, or Raman used to confirm IR result. And this will give more thorough particle characterization. And 532 is a commonly used Raman probe. Now we even offer a second probe, 785 nanometer for Raman, or the IR probe. So I'm going to talk about give some examples of the measurement. For example, here, this is a mix of polystyrene and PMMA, the microplastics, and it's dispersed in saline and then dried on the calcium fluoride substrate. And here in the middle is the optical image. You can see there are many particles, and we point out 9 of them, and the spectra on the left. You can see there are nearly 2 classes of particles. And then by tuning the laser to the 2 peaks, we can get this chemical image on the right. And the right and the blue, they are corresponding to different peaks, different wavelength. By comparing the middle, the optical image and the chemical image, you can see actually many particles are not present on the right. That's because then maybe the salt crystals that doesn't have the IR absorption of these 2 wavelengths. And what about bigger size? For example, here, this is a microplastic sample of particles that are as big as about hundreds of microns, or as small as 50 microns here. And on the right, I'm showing all the cascade spectra from these beads. You can see all of them have this exactly the same 2 peaks. And if we zoom in to check on one of them, you can see this is the IR spectra. And this can be searched against a database, and this is identified as polyethylene. And the Raman also can be used to search against the database. And look at how well the IR and the Raman spectra matches with the library spectrum. And also, it can provide the simultaneous ion and Raman for smaller particles. Previously, I showed like micron particles. Now, look at this one. This is a 500 nanometer microplastic, and we got the IR and the Raman. And if look at the second part, this is a cluster of these smaller beads, and the diameter is about 4 micron. And the iron spectra looks exactly the same as the smaller one. So the spectra from this technique is independent of the size. And all the spectra I'm showing here are raw and completely unprecise. You don't need to process the spectra again. And fluorescence can also be combined to leverage the specificity of the fluorescence. For example, here I'm showing an example of the polymers are stained with nanorite. But here you can see circled in green are the particles present in the sample but not fluorescently labeled. By using the fluorescence, we can only look at the 3 highlighted particles here and get the spectra, and then search against the and database to identify what are the 3 different particles are. So I'm going to talk a little bit about a new developed software that we used to automate the process that is called Feature Find IR. I'm going to stop sharing this PowerPoint and then jump to a video. So to show how it works. So this is how the feature finder IR works. It is for automated microplastic selection and measurement, and then identification using this microcam ID. So first, you have the sample loaded on the microscope. You can take find the focus, and then you can take a bright field imaging, where you can use this cross polarization, a patent pending and from PSC, and this will highlight the particles. And then you can take this highlighted imaging or bright field imaging input into this, and then you can put some threshold to select the particles you want to identify, or you can input here the size you want to measure. For example, here 2 to 40 microns. And then software will calculate where these particles are, the X, Y, the coordinates, also the size, the area, and then once you got all this, it's also interactive. You can select the particles you don't want, and then you input all these coordinates into the software, and then automatically click on the array selected. Now the first spectra, and then it will move to the next one, and then a third one. And you can see how fast it is. And a fourth one. So there are many in the field of view, you can see that. And this is all the result. After all the spectra, you can select them all and then identify them. And this is the result. So you can see there are many different kinds of microplastics in this sample. So that is how this feature finder works, and it can be used to improve the time efficiency. So I'm going to jump back to my slides and to give some examples of the samples. So this is one that the size the size that are defined here is 3 to 40 microns, and this crossed locations are the microplastics that are going to be identified, and this is the result. So using this microcam ID, and we can get the location and the identification, the ID of this microplastics here. You can see many, and they are colored actually according to their ID. So I want to point out to you here 2 features. One is the success rate. So the success rate here is almost about 80%. And it's interactive that you can even select, define the heat quality index. So this is all, we only identify in this case, the heat quality index that is above 0.5. And on the right is some of the spectra. And let's zoom in to check on some of them. For example, here I'm showing 5 spectra here, and they are all, as mentioned before, they're all raw and unprocessed. So you can see the size like 14 micron nylon and 30 micron polystyrene and 4 micron PI, and even for 3 micron PMMA and 20 micron PMMA, the spectra, the quality are the same. It doesn't change because of the size change. So let's look at some real world sample. This is a water sample that we got from the pier near Santa Barbara. You can see this is a bright field. It's very difficult to identify where the particles, and with the cross polarization, you can see the particles are actually highlighted. And then we can get using this feature finder to identify all these particles. And here showing one spectra of the HTP. And many of you probably noticed that actually in real world sample, not in addition to this microplastic, there are many other kinds of particles in the sample. So hopefully I convinced you that this OPTIR can provide submicron spatial resolution, and this will give the spectra that is FTIR transmission lag, artifact free, independent of size, and using a non-contact mode. It can also offer simultaneous IR and Raman from the same submicron spot, the same resolution. It can be combined with fluorescence to improve the time efficiency, and the spectra are directly searchable against the database. And this feature finder IR will automate the data connection and can give the hundreds of spectra per hour for microplastics that can be smaller than 20 microns. And a big shout out to my colleagues and our collaborators all over the world. And here's my contact information. Feel free to contact me if you have any questions after this meeting. And my colleague Jay and Owen are also in this meeting. So if there's questions I cannot answer, they can help. So we're happy to take any questions you have. Thank you.
Awesome, thank you, Ting. I think Shelley has her hand up.
Thank you, Ting. That was really interesting. I'm curious at how many different instrument companies have this type of technology. I just saw a presentation recently from Shimatsu, who also have a combination IR Raman instrument and also an automated sampling prep system. I'm just curious how those differ. And you said it can go lower than 40 microns. Can it go higher? So could you set it to like 4 to 400 or 4,000? You know, how you know, can really I really am intrigued because capturing both methods could be really powerful if you can capture that size range as well.
Yeah, so for that instrument, I think I will have Jay or Owen to answer you. And to the size part, I think it's not a problem to go from, as you mentioned, 4 to 4,000. That's not a problem. Hey, Jay and Owen, do you want to?
Hi, Shelley. Jay Anderson here. Hi.
Sorry, Jay.
Yeah, so again, the instrument that you're talking about, there are a couple of other instrument manufacturers who have recently introduced a microscope system that has IR and Raman capability on the same microscope system. But there differences between those microscope systems are the FTIR portion of that microscope system is still diffraction limited. So it's not going to measure on a smaller particle size. So you're still going to be limited on that system to the same diffraction limited if you had a standalone FTIR microscope system. So it's not going to improve the spatial resolution. The other thing that is typically going to happen with those types of systems is you're going to have a objective change between the Cassegrain objective and the Raman objective. So you may lose and have some differentiation as to the exact location that you're measuring. So in real world materials, oftentimes you have a fiber that you're measuring. And even if you take that same fiber and measure with an IR system and a Raman system, you may not be measuring on the same location, because again, if you use a 50x objective on the Raman microscope, you're going to be focusing that light down to probably less than a micron, to where the IR spot size is still going to be on the order of 20 microns. So exactly which location that you're hitting on is not going to be the same. In our system, all the measurements are done through the same objective, whether it's done for IR or Raman. So it's the exact same location, and it's the exact same measurement time. So our measurements are again, not diffraction limited. So we have the same spatial resolution, and we collect both the IR and the Raman data simultaneously, and they're not sequential.
Okay, and so let's say, like for example, the slide that Ting had, if you were to broaden that, let's say have a really, like the definition of microplastics for, the Department of Drinking Water at the State Water Board, if you were to broaden it to try to encapsulate that to the ability of the instrument, what would you estimate would be the time from start to finish to do the scan as well as generate the spectra and the data set?
Well, in the video that Ting showed, the measurements that you saw were actually real-time measurements. So typically when we're collecting a spectra, we're going to set the system up to collect a spectra in the order of a few seconds, typically going to be somewhere around 5 seconds. And in this slide that Ting just brought up, you have sort of a variance of 400 micron particle size all the way down to less than 10 micron particle size. So again, being able to measure the smaller and larger particles is very easy with the system. And again, we've done some experiments doing different testing to where one of my sample runs was, I think, 122 spectra and on the order of about 27 minutes. So it really depends on sort of the movement, how many samples you have, and again, what's your variance. We do a autofocus at each location, so we give you the best data at each of these points. So each measurement's going to take on the order of about 5 seconds. So multiply that by 10, 20, 100 spectra, 100 points, then that's going to give you your calculation.
Great.
But it's all automated.
And the reason I ask is because a lot of studies that we see, there's one scan, and Ting mentioned precision. So I'm wondering if you can take that, turn the slide 90 degrees or just as is, just do it all over again and generate a precision estimate. Are we getting to that point where we have enough time to do that because it's fast enough where we can do multiple scans? Do you see that? And have you done that? Have you generated precision estimates from your data?
I'll let maybe Owen add to that, but again, our system and our capability is all associated with being able to do very high spatial resolution imaging. So again, on our mapping stage, the same stage that's used to do this microplastic testing, the stage positioning is actually 50 nanometers as the smallest step size. So we have very precise capability to move the stage. So I don't know if Owen has done any precision experiments to sort of see the variance or not, but again, because of our sort of focus and high spatial resolution imaging, it's probably beyond what a lot of FTIR systems would have, just because they can't get to that small resolution, so their mapping stage doesn't have to be that precise.
Right. It's mostly the repeatability that I'm concerned with, and being able to, it depends on the technician and the instrument and the lab and all these factors. And so if you're able to show that you're able to get these repeatable measurements for the same sample, that's really huge. So yeah, that's what I'm looking for.
This is Owen here. I hope everybody can hear me. I just like to follow up on a couple of those questions. So, as Jay mentioned, we have the ability to collect, measurements on particles of various sizes. When you look at some of these broader FTIR studies, they're all looking at, really big particles, which take up a large portion of your field of view. But with the ability to sequentially filter, so the way these samples were prepared is they were filtered sequentially. So first there was a 20 micron filtration done, and everything that was above 20 microns, we didn't really necessarily care about in this study. Then we were filtered through onto an 800 nanometer filter paper, and that filter paper was then taken directly and measured itself. So there's no additional step after the filtration to actually collect the data. You can take the filter and put it directly into the microscope and measure on that. And obviously the time to data then depends on how many particles are identified. Now, Ting covered in her study when she talked there the ability to use different sort of masking techniques, be it, cross-polarizing images or fluorescent images if Nile red is staining. So obviously time to data is one of the crucial things in this field. And it's, something I've spent a lot of time trying to improve in our studies here. Because, there is so much stuff or junk on a filter paper that could be microplastic related or could not be. So, be it null red staining or be it cross-polarizing imaging, that can make, identifying what might be a plastic much, much faster. So that already eliminates a lot of the, other junk on the surface that's not microplastics. And then in terms of the repeatability, there's actually a small step missing from the video that was shown there, where we actually have a calibration step. So as soon as you transfer the data from what we call the feature finder, where you get that blob plot, into our software, the software actually shifts objectives and takes the image that we just captured, shows you a real live time image, and you click on the location of one of the plastics, center it in the image, and then the software automatically updates if there's any shift in crosshair positions, over time. The software automatically updates that. So in terms of precision, that's a step that's incorporated into the feature finder software itself already. It was just missing out of the video. So it's a very quick process that takes about 10 seconds. Once the objectives are changed and you click on a feature, and the stage automatically adjusts all the XY coordinates by that small shift amount, be it 1 micron or 500 nanometers. So I hope that answers the question, but I'm happy to take any follow-ups.
Yeah, I'd like to, chat with you afterwards. And, I don't think that's quite addressing what I was wondering about. I'm looking for, data on repeatability, sequential analyses of the same sample and what the outcome is at on a really much larger range of sizes in like a real world environmental sample. So I'll touch base with you guys. Thank you so much.
Yeah, thanks for your question.
Excellent. I think I saw some other hands up, but now I don't see them. So I think if you do have a question for Ting, please feel free to unmute. I don't know, Scott, how are we doing on time? Are we good to take a few more?
Yeah, we could take like 1 or 2 more.
Great. Does anyone have another question they want to ask? Yeah, I think I see Win has his hand up. Go ahead, Win.
Hey, yeah, really interesting approach. One question I had is it possible to do something like an LDIR with a Raman or with your OPTIR, where you kind of like probe the surface using a really rudimentary setting? You're just looking for kind of like some assessment of how much absorbance there is across the surface, and then create a map using that and find the particles that way. Is that like a possible approach with OPTIR, or maybe I just don't fully understand?
So yes, I think, for example, here you can see on the right, this is the IR image. It's tuned to a specific wavelength and then scan and then to get this image. This can also be used to map out where the particle is. Does that,
okay.
Yeah.
Oh, cool. Yeah, this is really cool. Thanks. Sorry, I think I just missed this part.
No.
Just to sort of follow up on that a little bit, there's sort of multiple size regimes to sort of consider here when we're talking about, microplastics. And, for us, we're certainly focused on the small stuff is the way I'd really put it. A typical, LiDAR system or something like that can do the big stuff very, very quickly, but it has no spectra from stuff, less than. So, we participated in the SQUIRP sort of round robin study in terms of IR and Raman analysis of these sort of spike test water samples. And, the result of those studies from the FTIR side of things that were collated was you can't really get super reliable information on things, above 20 microns, even all the way up to 50 microns. However, our focus is on the really, really small stuff. And correct me if I'm wrong, I believe drinking water filtration capabilities are already able to remove a lot of the particulate that's above 20 microns. And, so that's kind of where we're sort of coming from is the ability to do the really, really small stuff. As I mentioned, in the prep of these samples, all of the bigger stuff above 20 microns or so was removed by an additional filtration step. And we then just concentrated on the smaller microplastics. And you know, the database searching is actually our own database that we've made based off, you know, measurements on standardized samples from NIST. So you know, that's kind of the direction we're moving in is really in the very, very small stuff. Yes, we have the capability to take spectra on bigger particles, but you know, the time necessarily isn't as fast as some of the other systems. But then again, those other systems have absolutely no chance of measuring something that's sub 20 microns.
Excellent. Thank you
Thanks.
for that. And in case people missed that, Wynn was asking about LDIR, which is laser direct infrared, if you hadn't heard that term before. We have time for one more from Fred. Would you like to ask a question?
Yes, hi, hello, thank you. I'm calling in from Lodi, California. And I really appreciate your presentation. It reminds me of why I got a degree in chemistry, you know, it's very impactful, your work. So thank you. My question is with your instrument here, the identification, you've mentioned that in your database, like how many different microplastics are in your database?
So right
And
now,
does this include compostables? Is your
Yeah.
database? Oh, that's my question.
So right now, the database consists of about 25 of the most common microplastics, plus a lot of reference spectra for what we would consider, you know, not microplastic, but commonly there, you know, sand, shell, bone, things like that. So we have all of those as references as well. But the nice thing about the software is we have the capability to add additional spectra. So the user themselves can take a spectrum on the OPTIR system on a known plastic and then add that into the database if they want to. So, you know, that's kind of the way it's working at the moment. And yeah, if there's any follow-ups, I'm happy to answer them as well.
We can also, in the aspect of that, this is Jay Anderson, Fred, also to follow up on Owen's comments. Again, the spectra that we collect is FTI or transmission quality like spectrum, and that spectra is directly importable into Know-It-All, and we can use the Know-It-All libraries. There are also libraries such as the one that Wynn Gallagher and others are working that are open source. So the data can be directly imported, and we can utilize those types of spectra also. So it's really, we have our own database that we've started to create built into our software. But again, those third-party and open source codes are available.
Looks like we have a hand from Max, maybe not.
Yes. Yeah. Thank you very much for the presentation. This is Max Zarate Bermudez from the CDC. Quick question on the plots presented today and the graphs. Did you use synthetic samples and real samples for this? Can you please tell us about that?
Yeah, so so I think there was 2 data sets shown. One was a real world sample. That was the sort of second to last slide that Ting showed, I believe. And what that sample was is one of our colleagues went down to Goleta Pier with a paint bucket and dropped it off the edge of the pier, picked up, you know, a full gallon of water or so, and we just then filtered that through our sequential filtration technique. And, you know, there was maybe only 4 or 5 plastics identified in that run, which was, you know, polyethylene. I believe there was also some polystyrene and things like that. And then the second sample that was shown was a sample that we made ourselves, but it wasn't, we didn't want to use spherical particles. We wanted to use sort of something more realistic. So what we did was we went around the lab and found a bunch of material that we sort of knew the composition of, or we knew it was a plastic, and then we shaved it, put it in water, and then filtered it down. And so we obviously shaved it and sonicated it to many sizes, but we wanted it to be an approximation of a real world sample in terms of, you know, rough edges, you know, not smooth spheres, all that kind of stuff. That's kind of what we initially developed a lot of this software on, is just using, you know, 5 micron or 1 micron polystyrene spheres, but that's not, hugely real world example-esque. So that's why we decided to do this sort of additional sort of filing and sonication to make a pseudo real world sample, but it was just made in the lab. But the other data that Ting showed was taken directly out of the seawater from Goleta. And if you look at the analysis of that, there's a lot of sand found, there's a lot of bone found, a lot of shell fragments and things like that, which are all identified by the software as well. But there was only really 3 or 4 microplastics found per that about gallon of water.
Thank you very much. I missed that during the presentation. I appreciate it.
No problem.
Excellent. Thank you all. And thank you, Ting, for this wonderful presentation. Ting, if you want, you're welcome to put your email in the chat. So if people have more questions, they can email you.
Yeah.
But I suggest we move on to our next presenter. We will be hearing from Zehui and Lisa on their rapid microplastic analysis with nanopore sensors. Sorry for mispronouncing your name.
Oh, no, that's fine. Thank you, Monica. Okay, let me share my screen. Okay. Okay. Okay, so can everyone see my screen? Let me go to. Okay, so everyone see my screen?
Looks great.
Okay, cool. Okay, thank you everyone for, good morning everyone. It's an honor to be here and present our work on detecting nanoplastics with the advanced solid-state nanopore sensors. And let me briefly introduce our company, GoPert. So GoPert was founded in 2018 by Professor Maria Darndich from Department of Physics at UPenn. We are located in Philadelphia, and right now, as a startup company, we have 4 PhD level research and development scientists and 2 lab technicians. So our core technology includes the solid-state nanopore chips, single molecule diagnostic, nanopore sensing, and advanced materials like 2-dimensional ones. And we have received fundings from NASA, NIH, NOAA, and the Children's Hospital of Philadelphia. So most of our funding are through the SBIR and STTR, which stand for Small Business Innovation Research and the Small Business Technology Transfer programs. So what is a nanopore and how it can be applied for detection purpose? So a nanopore is a nano-sized or larger pore, which is usually from a few nanometers to a few hundred nanometers. It's a hole drilled in an inorganic material such as silicon oxide or silicon nitride. So the nanopore-based technique, the nanopore-based detection is a single particle detection technique because only one particle is allowed to pass through the pore at one time. So when there's, in the absence of the particle, the current is flat. Let me show you. Okay, it's Lisa. The current is flat, and only the small ions like potassium chloride will pass through the pore. And when the particle is passing through the pore, it causes the blockage of the ion currents. That formulates like a current blockage, which we already call an event of the translocate of the current change. And by further analyzing the characteristic of this current spike, such as the amplitude or the duration of this event, we can get the information like the size, the charge of this translocation particle. So the nanopore technique features an all-electrical single particle sensing technique. And on the picture on the right side is the nanopore detection instrument we daily used. So in the nanopore, it is a very compact, portable, and easy to use instrument. So usually once we have this nanopore chip, I mean, it's a really small, like 5 by 5 millimeter. So we already insert a nanopore chip into the fluidic cell, and the fluidic cell will be further inserted into the nanopore reader. Now, the nanopore reader is really small; it's only centimeter size. Fit into your pocket. It's a USB drive in small instrument. And this is typically what we use for detecting, widely used in all of our projects. And here is the slides we show how we usually manufacture a nanopore sensor. So we typically follow a standard semiconductor manufacturing process. This process usually in a wafer scaled process. This usually involves the multiple complex process, such as the etching, the exposure, the coating, and stripping, and etc. So, but the purpose is we drill the we process the wafer, and then we dice the wafer into this 5 by 5 millimeter chip, and then we drill a nanopore in the center of the chip. So on the picture on the very right side is the transmission electron microscope image showing a 900 nanometers nanopore drilled in the center of this chip. And this is a very complicated and semiconductor involved process. So only a very few commercial available vendors sell this nanopore product in the market now. And how can nanopores used for nanoplastic detection? So the current analysis method involves the visual inspection, the microscope, spectroscopy, and mass spec. So all this technique, they have their own advantage. They have shown their ability of detecting nanoplastics either at higher spatial resolution or increased sensitivity. But very few of them are capable of detecting capable of rapid detection of smaller particles using a very small portable instruments, which can be further deployed for field use. So in our work, we applied the nanopore sensors for detecting some nanoplastic bits. So this work was funded by NOAA SBIR Phase 1 program. In this project, our work is to develop a proof of concept platform for nanoplastic detection based on the solid state nanopore techniques. So in this project, we used which was very simple NIST traceable polystyrene bins from 100 nanometers to 750 nanometers. And we manufacture nanopores from 100 nanometers to 1,000 nanometers diameter. For the solution, we choose the simplest of just use DI water and those 10 millimolar potassium chloride for the detection to create the ion flow. And next, I want to show how we validate the nanopore sensors. First, I want to show here is the sensitivity of the nanopore sensor. So on the left side, the ABCD4 figures are the real-time current change versus the time traces of the polystyrene of a 500 nanometers polystyrene translocating through a 600 nanometers nanopore. So we start with 30 ppm and gradually lower it to 0.3 ppm. So for the figure here, each downward going spike here represents the translocation of one polystyrene beam through the pore. We can see in all ABCD4 figures, the current change are very uniform. The delta I is almost is between -15 to -20, which means the pore is very stable during the measurements. Excuse me. And we also see the number of the current spike here is correlated with the concentration. It's concentration dependent. And they also distinguishable signals at different concentrations. And if we calculate the number of these current spikes, which means the number of the events per second versus the concentration, we can get a linear correlation between these two parameters. And the R-square value is 0.99, which is really good. And potentially we can use this standard curve to calculate the number of to calculate the concentration of polystyrene beads in an unknown sample. And next, we want to validate the specificity of the nanopore. So in this one, we mixed the polystyrene beads of different sizes. Like, for example, in A, we mixed 100 to 200 nanometers, and here is still the same, it's still the real-time current traces versus time. And in B, we mixed 100 nanometers with 500 nanometers. And also in the right-hand two figures, we draw a scatter plot of the current blockage, which is the amplitude of this current spike versus the dwell time. Dwell time is how long this current spike is. And for each mixture, we can see clearly the grouping. We can clearly see the grouping behavior of these particles. So one plot here means one particle translocation. And if we calculate this scatter plot, the number here is roughly correlated with the concentration of this mixture. So this means our nanopores can detect and differentiate the particles of different sizes. And so previously, I show a lot of these downward going current spikes, which are correlated to the negative polystyrene beads. And if we reverse the voltage and apply some negative voltage, we can detect the positive polystyrene bead as well. In this scenario, the current spikes will be going upwards. So by reversing the voltage, we can detect either both positive and negative polystyrene beads. And another result we achieve here is about the nanopore cleaning and unclogging, and most importantly, the reuse of the pore. So here we demonstrate the nanopore cleaning by using a simple UV ozone lamp. So we buy this lamp from Amazon and just install it in the shoebox. We just put the nanopore chips here and let them react for 1.5 hours. And in this column, you can see before the cleaning, like showing in the blue column here, the pore is barely opened. There's no ion translocating, there's no ion flow the pore. But after cleaning, the pore is properly wetted, and it can let the ion and let the ion flow pass through the pore. So the cleaning pore is very important because first it can provide reliable results. Second, it can significantly decrease the mirror noise in the downstream measurements. And once after cleaning the nanopore and when we apply it to the measurements, another thing we want to avoid is the clogging of the pore. You can see here, say without clogging, the current is very stable, like horizontal. But once there's a pore clogging, the current drop immediately. Sometimes we can resolve this clogging by reverse the voltage, but sometimes, like towards the end of this measurement, the pore clogging is permanently. You have to take the chip out and re-clean it. And so then we figure out like we should find an easy way to solve the nanopore clogging. Of course, by the cleaning is a good way. But then we try to figure out another alternative, which is by baking. So simply we just put the nanopore sensors in the furnace oven and bake at 450 Celsius for up to an hour. You can see like before we bake it, like showing in this orange column here on the bottom right, the pore is clogged. The diameter is significantly decreased. But after baking, the diameter all went back to their original diameter, and there is no pore there's no pore like expansion or breaking from this method. So we think this unclogging method is very useful because it prove like first our pore is very robust. It can withstand like even 450 Celsius degrees. Second, it can be reused multiple times. And another thing which is really important is after getting the data, you need to analyze the data. So by analyzing the data, we can get a concentration, size, and some general information of the particles translocating through the pore. So previously, we manually, you can see all these current spikes, we manually pick each event by eye and manually analyze them, which is very time consuming and labor intense. For example, for this current probably not this, for here we show an example like for the same current traces, we were able to by hand manually identify 40 translocation events within 2 hours. This is really like time consuming. But then we develop a few algorithms, which is specific for the nanopore analysis, and we were able to detect up to 5,000 translocation events within only 20 minutes. And this two grouping, the distinguishable grouping events matches both the manual and automated data, automated softwares. So we're now still on the process of advancing, upgrading these algorithms. So one day we can realize this very fast, reliable data analysis and with minimal manual intervention. And here I just briefly show like how the cost of our instrument. So our instrument basically has 3 key components, which is the nanopore chip, reader, and flow cell. So the nanopore chip is only 5 by 5 millimeter, and the price of a chip is about $70. And like I showed before, it can be cleaned, can be baked, and it's pretty robust and allows for multiple use. The chip can be disposed only when it's broken or is significantly expanded. And for the nanopore reader, its centimeter size can fit into your pocket, is about $8,000, and also allows for a very long time usage. And the fluidic cell is all 3D printed, and it's very small too. It's about $400. So we have been using the same flow cell for like a year now. So all these are pretty robust and can withstand quite a long time. And this is a prototype we have in mind. This is a rendering prototype we have in mind for the nanoplastic detection, from the sample collecting, sample loading, sample adding, and running the sample to the final data visualization. We are picturing our instrument to include the flow cell, nanopore, the data, the instrument itself, and a data processing software. And we welcome all kinds of collaborations, opportunities, and would like to see how our technology can help and fit into the California Water Board goals. And this work was funded by the NOAA SBIR Phase 1 program. And this is the website of our company. And if you have any questions, you can email to ask me or my colleague Lisa, who is also at this meeting right now. Okay, so that's the end of my presentation. Thank you very much.
Excellent. Thank you so much for that wonderful presentation. Are there any questions? Either unmute yourself, raise your hand. Yeah, Dr. Cover.
Yeah, thanks. This is a really cool technology. Definitely seems like it unlocks a lot of new avenues for research and management. One thing that I was wondering, I might have missed it, but is there a way to tune the specificity of this device to different polymers? So for example, like, can I just say I only care about polyethylene? Can I tune it so that only polyethylenes are getting measured?
it is feasible. So right now in our phase 1, we choose this either positive charge or negative charge because our instrument is all electrical. So as long as the particle has charge on the surface, it can be detected. And if the particle is not charged, we can go back to the literature and find some way to treat this particle. For example, like you mentioned, if we want to, for example, like if we want to differentiate the PET from PVC, like because these two different polymers, they have different resistance to alkali, to different basic solutions. So we can compare the signals before and after treating these samples and compare these two signals and see if we can get a difference. And this difference can be related to the property of different polymers.
Right, yeah, that makes sense. So there'll kind of be like custom built pre-processing routines for different scenarios. Yeah, cool.
Yeah.
Awesome, thank you.
Yeah. Oh, that's one. So our technology is more like try to get a large particle distribution because that's the powerful point of our. You can get different particles because different particles, when they pass through the pore, they will have different current amplitude or dwell time. So that's very accurate information, like particle distribution. Yes.
Excellent. Any other questions?
Yeah, I just have a quick question, I guess. It just sort of concerns pore clogging.
Mm-hmm.
How quickly do they clog up? Because I can imagine if you put a real, world seawater sample in there, a few grains of salt might clog the pores. Is that a possibility?
Yeah, that's a good question. So I think what it comes, because like right now we already use like very clean system, just polystyrene standard base. Yeah, like you said, when it comes to a real water sample, it can be tricky. So that's why it probably will require a lot of pre-treatment like ultracentrifuge or filtration of these samples. Just so we know the size of the sample won't clog the pore. For example, if you use like 500 nanometers pore, but some of your sample is 800 nanometers, so definitely it will clog the pore. So we probably will have lots of like investigation of the pre-treatment of the samples to make sure they are not clogging the pore. Okay, thank you.
So I'll ask a question. Is it possible to perhaps use this for, I guess I'm thinking of like a way to like subsample a sample. So let's say I wanted to focus on below a certain size fraction. Could I somehow like introduce like a filter at the end of this process or something else, then I can take it and then do pyrolysis GCMS on the particles? Or is there a way I'll stop there.
Yeah, thank you. That's a good question. So that's one of our filter go-to. It's more like we want to have an array system, like more like filtration, 500, 400, 300, 200. Let this sample go through this. So each time it's more like filter the larger particles and only like the smaller particles go through to the downstream. Yeah, it's totally doable. Like because we are capable of manufacturing nanopores of various size, like the size at our will. So this can be like an array, like a downstream system, stepwise filtering the sample. So yeah, it's totally feasible.
Thanks, Shelley.
Thank you so much for your presentation. That was really interesting. I'll just ask a similar question to what I asked the other presenter. Have you done any studies on repeatability for your technology?
Yes, well, for this sensitivity, we have repeated this multiple times on multiple chips, so we keep seeing the same signal again and again.
Have you done it for anything besides polystyrene? Have you done like other polymers or mixed polymers?
Yeah, that's a good question. So because this work, like I show here, is based on a phase 1 program, so it's only 6 months long. So we are looking forward to achieve more technical goals, like it's a mixture of polymers of different sizes, different categories, or even different shape, like beads, rods, and then couple them with different nanopores. So yeah, that's on our phase 2 plan as well.
Fantastic.
Yeah.
Thank you.
Thank you.
Jane, do you have a question?
Oh yeah. Thanks for the presentation. I just want to know, like, when you said this nanopore, this is it stretchable? And if it is, like, after how many repetition or how much use you need to replace the nanopore? Thank you.
Yeah, okay, so the nanopore we have is a silicon nitride, so it's not stretchable. I know, like, some polymer-based nanopores, they are stretchable, like PU-based, but our pore is, so because we already fabricate using the ion beam or electron beam, so once it's made, it's fixed right there.
Thanks.
Yeah, okay, thank you.
Excellent. I think we have time for one more question. All right, not seeing anything in the chat or anyone unmuting themselves. Thank you again for this wonderful presentation. And if you want to put your email in the chat, that way people can contact you. Otherwise, I'll turn it over to Scott for what do we have next? I think group updates. Yeah.
Okay. So we do have a bio break on the schedule, which we are a little bit behind schedule for. So maybe people need to go to the bathroom or something, you're on Zoom. So take a little moment if you can. So we're just gonna go right into the consumer work group update, and then we'll hear from Shelley Walder about the sampling playbook work group, and then Dr. Wynn Calger about data and lab accreditation. So unfortunately, Brent couldn't be able to make it today. He is the lead for the consumer messaging work group. I'm part of that work group, so I'm just going to provide a really brief update. So the goals of this work group is to assist the drinking water utilities in having some resources to communicate to consumers about the state's microplastics monitoring we'll be doing. And currently, we are requiring that the water systems that monitor for microplastics in their source waters include their findings in their annual consumer confidence reports. And we are working as a group to develop some language that these water systems can throw into that consumer confidence report if they prefer. And the CCR language modules that we developed were for 6 different topics, covering really the breadth of the microplastics relation to drinking water. So, the health effects, about treatment and monitoring, and what this might mean for different utilities. Each of the work groups working on that have completed their topic statements, and we'll be presenting that to the rest of the group like at the next meeting. We're working on getting some references and citations for those, and really finalizing those modules. And then Brent is working on an introduction and a preamble to accompany those modules. So something that would describe the purpose and their intent, really just to provide a full picture and full playbook for the water systems. We don't have a date set for the next call, I believe, but we do intend to describe the logistics of what to do with this information, how and where to post the information, advertise it, get the resources out. So if anyone is interested in that, please let me know. We can get you on the email list for that particular work group. And next, I'm going to go over to Shelley Walder, the sampling playbook, provide a brief update.
Thanks, Scott. Let me just pull our presentation up, make sure I'm on the right one. Okay, bear with me a moment. All right, how's that looking? All right, great.
Looks great.
So it's great to be with you all again. I always look forward to these meetings. Shelley and I have just a very brief update for you. So hopefully we can help everyone catch up on our timeline. So as a recap, the Microplastics Monitoring Playbook, or MPMP as we like to call it, it's focused on sampling and analysis, not only analysis in the lab, but data analysis. And we're really excited to bring this all together. The Moore Institute's work that they're doing on the data portal is going to be really great to help round this out. So as a background, Shelley Moore worked on the California Trash Monitoring Playbook, and it's based on the best available science and builds on lessons learned. So we're not trying to reinvent the wheel. We want to bring together in a usable format and a community that we can really build on this stuff. And we want to make sure that it's question-driven, evidence-based, and statistically rigorous. That last part is really tricky when it comes to microplastics, because if the method is really expensive and takes a really long time for every particle, the budget will dictate that there are fewer samples analyzed, and that increases your uncertainty. And so and you can get orders of magnitude difference in your results based on your data quality. So that's no matter what matrix we're talking about, that is key. So that's why I got really excited when I hear that there's some methods that are a little faster, can do a lot more in less time, and maybe less personnel to run it. So we'd shared before our general outline of what the MPMP might entail, including everything from some common vocabulary to what method, decision processes, how you would decide what method to use, how that data capture would look like, how would you report your findings and conclusions, and then some tools and references that you would be able to look at within the document. And this is a living document. So, this is, as the field is evolving, so would these types of resources. So again, we're talking about measurement uncertainty. If you measure it once and then measure it again, you could have very different results. So we want to make sure that we account for that. And luckily, Wagner et al. Did a great job kind of looking at that. Jeff Wagner is with the California Department of Health, and they did a study with Bill Robertson and Harry Allen of EPA Region 9. Bill is the lead for the ASTM Microplastics Subcommittee. And so they're really trying to get at how to account for uncertainty in your measurements, no matter whether you're looking at counts or mass-based. So that's exciting, because as we know, as Scott has presented, we're looking at something that's a tiered monitoring framework. And so we can take lessons learned from studies like this and apply them and then give you guidance through the MPMP. So just as a background, just recap the precision, you would take a relative standard deviation from multiple measurements, but you don't necessarily need to make those measurements yourself. If you have a similar instrument or data set from a similar water body or environment, you may be able to take the variability from those data and incorporate that into your own, therefore not having to run things 7 times. Maybe you would only have to run it a couple times to help get your estimate and incorporate those data and streamline the process even further. So those are the kinds of guidance that will be in our playbook. And like I said, it's using both count-based or mass-based. I think with this first round, we'll be giving you a lot of count-based guidance, because that's what the drinking water folks are going to be focused on for now. And this is, sorry, I don't have a reference here, but This is something that Scott's presented in the past, and it's the tiered monitoring framework that we're all pretty familiar with, where tier 2 is something like pyrolysis GCMS, or another way of measuring microplastics by mass. And then if they pass a certain threshold, then we're looking at individual particles. So a lot of it has been focused on this tier 3. And so we want to make sure that we're covering all the tiers as time goes on. So, you know, when we have things like counts, we need to have sorts of rules of how you're counting. Are you going to be, how you're subsampling, that kind of thing, and giving that kind of guidance depending on whether it's an air sample, it's a water sample, it's a biosolid sample, it's a soil, or whatever it is, and incorporating that into the method. So Shelley and I have been working with Harry Allen on data quality objectives. He recently drafted one for particles using, I'm sorry, not particles, for sediments and biosolids using a mass-based. And, but we also have been working with him on particle-based. So we're coming along with that, and we're still looking at sometime this fall to roll out some drafts of some of this stuff. So, and then in the other realms of microplastics beyond the MPMP, I'm still working on sample collection and analysis methods for biosolids. I recently took a tour of a wastewater treatment plant and looked at the different treatment trains of the plant and where biosolids would be sampled and how that might work. Lots of literature review for that. Working with University of Pacific and UCI on some of their techniques that they're going to be using for biosolids, and trying to incorporate that precision estimate approach, make sure that we have that so it's a robust study. And ASTM had their, the D19 committee had their June meeting, and the pyrolysis GCMS method was discussed for a while. There were very specific terms like sample, instantaneous, vessel, cup, things like that are holding up the method. And it's a little, the method's not changing, and it hasn't changed, but it just needs to go through balloting and make sure that all of the instrument companies are happy that it can be very generalized to apply to anyone who can do pyrolysis GCMS with their instrument. So that's kind of the holdup with that. And but it's ready to go. So if you have a draft, you have the method, you know, plus or minus the word vessel or sample or cup. So that is coming along, and I'm really excited to be able to announce, you know, when that's finalized. But again, it's just, it'll be on the website as finalized and something that can be available. But it is, if you're on the committee, you have the method that's whenever it goes to ballot. And that's all we have for now. We're excited to reconvene at the next meeting. I think we're going to get together with the Microplastics Subcommittee co-chairs, and we have a really exciting lineup to hopefully bring to you for speakers that we're very excited about. So that's all I have.
Thanks so much, Shelley. Does anyone have any questions? Anything to add?
See something in the chat. Thank you for the reference, Scott.
Alrighty, well, if we don't have any questions or anything else, then I will hand it over to Dr. Wynn Cowger to provide an update on the data and lab accreditation workgroup.
Thank you. I'll share my screen real quick. Let's see here. Is that sharing? Can you all see my screen now? Thanks. So this is a little bit of an updated data validator workflow. I just want to remind everybody about the overall goal of this is to get data from accredited labs who are accredited to sample for microplastics in drinking water into public hands, into policymakers' hands, into management hands as quickly and easy as possible. And so to do that, we have developed a portal we are now naming One for All, because the big goal of this is to be one portal where you can share any type of microplastic data, not just tabular data. You can share spectra, images, everything like that. And that it can very quickly tune to be customized for specific projects. So maybe you just care about images, maybe you just care about spectra. We want people to be able to reuse this tool. It's open source. A couple of other updates. So we're still working on integrations with Tomex and OpenSpec, also the trash taxonomy and some of the other projects that we've talked about in the past. We have now changed up our backend a little bit. So we have Amazon S3 where we're storing all of the data, and that's going to be like our own repo. But then also data is going to data.ca.gov. And previously we had mentioned that one of the goals was to get data to CDIN and CIDWIS. But I think now, after talking with the curators there, that may not actually be the end goal, because they're quite happy with the data being curated and then going directly to data.ca.gov, from what I can tell. That may change in the future, but I also wanted to give a little demo real quick of some of the new functionality. So we now have a data downloader. So this is the data upload portal. When you upload data, for example, let's see here. So we upload data here, and then you can input a key if you have one. We also have an option to turn off this key if you just want your portal to not have like a security feature. Okay. I'm having a bit of an error, one sec. Everything breaks when you try to show it off. Oh. What's happening? Yeah, I think the screen share was preventing me from being able to click anything, so I had to turn that off. That was interesting. So anyways, so we also have a data download feature now, where you can basically here. Okay, you can download your data. So whenever you have a data set, we digest that into a unique key, and then you can call for that key from our repo and download it as a zip folder again. So this is really a long-term storage place for any accredited labs to store their data. They don't necessarily have to have additional copies and backups, because this is going to be a really good backup for them. It's backed up in several places. And this will be hosted long-term. Let's see, what else have we done? I remember the other thing. The last thing I wanted to talk about was there was a publication that came out earlier this year from researchers primarily out in Europe, who have developed a database schema for microplastics in the environment. I think it also applies quite well for microplastics in drinking water. Their schema is intense. Like this is their diagram here. So this is what the database is going to look like. Scott and I are currently working on figuring out how to take those Excel files and CSVs and convert them into this database. So really our goal with the data portal is to make people sharing data with us really easy. It doesn't necessarily mean that it's going to make our jobs easy managing this massive database, but that's okay. You know, we just want people to be able to share data. And so we're going to figure out how to get our data format into this database so that it can be rapidly queried. They've gone through a lot of effort to make this database useful for a really wide swath of problems in microplastics research. So I think we're gonna go ahead and move forward with this and start working on that as our next step.
Awesome, thanks for sharing, Lynn. Does anyone have any questions or anything to add? Shelley, go ahead.
Thanks, Scott. Great presentation, Wynn. It's really exciting to see that you're, seeing what else is out there and building and collaborating. I just love that. Thank you. And I was just curious with the other. I haven't read that paper yet. I did see it, but do they have? Is it all count? Is it all individual particle based, or are there also like mass estimate kind of things in there as well, or for polymer ID?
The coolest thing is that they came to the same schema as we did independently. And that's really exciting because I think that really that was like a validation step for me. When I read that paper, I was like, oh my gosh, they have the same exact schema. I mean, it's not the same exact terms and everything, but the structure is the same. They have a particle level table, they have a sample level table, and then they have a methodology level table. And you can think about it all like that. All the other little subtables, those are really just for efficiency in mining the data out of the database. So yeah, they can go all the way down to the particle level. They can characterize, any sort of particle unit that you want, particle shape, size, color, mass.
Okay, great, thanks.
Yeah. Yeah, thanks for sharing that link, Monica.
Alrighty, well, if we don't have any more questions or anything to add for that particular topic, we can move over to our last agenda item, which is really just a forum for open discussion, updates. If anyone wants to share other things happening in the microplastics community, upcoming webinars or workshops or meetings or conferences, really anything you want to throw out there, now is the time to do it.
Is Caitlin still on? Okay, well, I was just going to.
Sorry, Shelley. Yes, I am.
Oh, yeah. Do you want to make a pitch for the upcoming OPC meeting? I know you guys have some big announcements.
Yes, absolutely. That was included in the agency updates at the beginning of this meeting. We have our council meeting. It takes place quarterly. We have our next council meeting next Tuesday. That is August 15th. With 2 items related to microplastics. One is the approval of funding for the 5 selected competed research projects that were identified earlier, as well as an augmentation to an existing grant with the Southern California Coastal Water Research Project, known as SCORP, related to analyzing microplastic samples that are collected through the regional bite monitoring program.
Thanks, Caitlin.
So,
also, the collaborative effort between OPC and the NOAA Marine Debris Program, they're having their individual work group meetings for the summer. I think it's the 3rd week of August. I know Goal 5 is on the 21st, and I'm sure the other ones, they usually have them all around the same couple weeks. So be looking out for those. And if anyone has a link, we can share to get people on board if they're not already linked into those meetings. They're really great. So they're very focused on different categories of topics, and microplastics would be mostly goal 4, but can also span into goal 5 and others too.
Thank you, Shelley. We'll be having those posted on the project website fairly imminently. So Scott, I'm more than happy to share that for this listserv.
Thank you, Caitlin.
Thank you, Caitlin.
Alrighty, one last call for any updates or questions, open dialogue, to share or ask. Alrighty, well, thank you everyone for joining our August meeting of the subcommittee. And thank you all the speakers that came today and provided that amazing information. I'll be sending out a calendar invite for the next quarterly meeting next week or two, so look out for that. And wish you all a happy rest of your Monday.
Thank you. Bye.
Thank you,
everyone.
everyone.
Bye, everyone.